Hello, everyone. My name is Deepti from Johns Hopkins University, and today I'll be presenting our work, Attentive Prototypes for Source-Free Unsupervised Domain-Adaptive 3D Object Detection. LiDAR datasets have facilitated the development of extremely effective data-driven perception algorithms for autonomous driving, but they come with their own set of challenges. The weather conditions and locations of data capture lead to biases in the datasets due to the specific dimensions of roads, vehicles, and the driving conventions of the area, leading to distribution shifts between datasets. 3D object detection networks tend to be biased towards the data they're trained on. It has been demonstrated that the evaluation on datasets captured in different locations, conditions, or with sensors of different specifications than that of the training data results in a drop in model performance due to the domain gap with the test or target data. Unsupervised domain adaptation has been broadly successful in addressing this problem for both 2D and 3D object detection networks, but depends on the annotated source domain data during adaptation, limiting its applicability in scenarios where it is unavailable due to the privacy concerns or memory constraints. Recently, an alternate source-free setting for domain adaptation has been proposed in which the source-trained model is adapted by training only on the unlabeled target distribution samples. Pseudo-label-based self-training has been successful in unsupervised and semi-supervised domain adaptive works and lends itself to the setting of source-free adaptation. In this approach, the predictions of the source model are utilized as pseudo-labels to supervise the network on unannotated target data. However, current self-training based methods rely on confidence thresholding to filter noisy pseudo-labels. As illustrated in this figure, the use of high thresholds as is general practice results in training the model on easy samples and incorrect labels of high confidence that contribute to the enforcement of errors during adaptation. We suggest that a self-training framework that can deal with label noise that requires only pseudo-annotated target data is an effective strategy for source-free domain adaptation. In the presence of label noise, standard feature aggregation methods of prototype computation are ineffective since features corresponding to incorrectly labeled regions could contribute to the final prototype. This is illustrated in the left side of this figure. Equal importance is given to all annotated regions during aggregation, resulting in the corrupted class prototypes in the presence of noise. Inspired by the high representative power of self-attention and recent works that make use of transformers to focus on salient inputs, we calculate an attentive class prototype by using a transformer to identify salient regions of interest and combine their associated feature vectors using prediction entropy weights that represent the uncertainty of the classification branch for each sample. We propose the attentive prototype for learning representative class features in the presence of label noise by leveraging self-attention through a transformer block and perform source-free, unsupervised domain adaptation of 3D object detection networks that mitigates the effect of label noise during self-training by filtering incorrect annotations. This is a visual overview of the proposed domain adaptation framework. The object detector is initialized with the source-trained model and used for region proposal and feature extraction by the domain adaptation block. This consists of a transformer module to generate attentive features, prototype computation, and the calculation of output classification loss weights using cosine similarity. The network is initialized with the source-trained model and trained on the pseudo-annotated target data. Every k iterations, the network is inferenced to obtain predictions that are filtered by a low threshold value t, which are then used to update the pseudo-ground truth annotations. In this way, the network is supervised by progressively refined pseudo-labels. The attentive prototype is the entropy weight average of the attentive region of interest features. Each attentive prototype is computed in an iteration combined with the prototype computed in the previous iteration through exponential moving average. Once the representative class prototype is obtained, we use it as a soft filter to identify region features that are dissimilar and thus far away from each other in the feature space. With this similarity-based downweighing, the losses corresponding to regions that have been identified as incorrect through prototype matching will be downweighed and not contribute to training. As the representative prototype improves with each epoch, the network becomes better at soft filtering incorrect regions and avoids reinforcing the error in pseudo-labels. We demonstrate the results of our domain adaptation framework on two object detection networks, second IAU and PointRCNN, and compare it against four domain adaptation methods. Direct transfer, which is inference of the source trained model on the target data, ST3D and SFUDA3D, current source-free unsupervised domain adaptive works. statistical normalization, a weakly supervised approach that uses target domain bounding box statistics, and pseudo-label self-training, which includes retraining the object detector on thresholded source model generated pseudo-labels. For reference, we also compare it with the Oracle results, which are obtained by training the detector on ground truth labels of target domain data, indicating the possible upper bound of performance after adaptation. We find that we outperform the current state of the art in most settings. Further demonstrate the effectiveness of our domain adaptation framework with those of recent methods through a visual comparison of the predicted bounding boxes for the Waymo to KITTI task for both object detection networks. Problems of direct transfer of the source model are localization and overconfident false positives. Objects such as large vans are incorrectly identified as car. This problem is mitigated only partially by labeling methods and by SD3D and is better addressed by our approach. We also demonstrate improved localization of correctly classified objects. In order to visualize the quality of the pseudo-labels at different stages of training, we plot the confidence score histogram of 500 correct and incorrect pseudo-labels generated by the source-only model and 3 consecutive meta-iterations. In the case of correct pseudo-labels, which are indicated with an IOU threshold, IOU value greater than 0.6, we desire that the model generates confident labels with higher IOU scores. And in the case of incorrect pseudo-labels, be uncertain about the generated labels with low IOU scores. This means that the distribution should lean left. We observe this in the labels generated after adaptation. They are less noisy than that of the source-generated labels, indicated by the fact that incorrect samples of meta-iteration 3 tend to be distributed with a lower confidence than that of the direct transfer labels. This shows that the quality of the pseudo-labels improved after adaptation using our method. Thank you.